In this screencast I'm going to solve this first order differential equation, and I'm going to use the method of separation of variables. The reason for that is that this differential equation is in the form dy by dx equals a function of x only multiplied by a function of y only. It's already in this form, hopefully you can see this. The function of x in this case is just x, and the function of y is y squared minus 2y plus 2. I might have had to do some rearranging to get my equation in this form, but it's already here, so I can proceed immediately. And what we do for that is separate the variables, so I'm wanting to bring all the y's over to the left-hand side with the dy, and I'm left on the right-hand side with just x dx. Now what I have to do is integrate each side separately with respect to its own variable, and then at the end I can hopefully rearrange to make y the subject, although sometimes that's not possible. Now the right hand side is fairly straightforward, so I'm going to do that first. The right hand side is just the integral of x dx, which is x squared over 2. I'll put the plus c in here. The c is the constant of integration. We also need one on the left hand side, but I can then combine them into one. So in the end we'll only in fact have one constant of integration. Anyway, that's the right hand side integrated. The left hand side needs quite a bit more care, so I'm going to proceed fairly slowly with that. The left hand side is the integral of 1 over y squared minus 2y plus 2 dy. And I have a quadratic on the bottom there in the denominator. And one way to proceed here is to complete the square in the denominator and then use a standard integral result. So that's what I'm going to do here. I'm going to complete the square all in one go, but if you're not able to do this, you could do this separately and then put the result in afterwards. What I do to complete the square is I look at the coefficient of the y term, which in my case it's minus 2, so I divide by 2 and I get a minus 1. And if I square that bracket out, I get y squared minus 2y plus 1. So in order to get a plus 2, I need to add another 1. And you can check that's right if you want to by multiplying it out. So now what I'm going to want to do is use a standard integral, and I'm just going to write down what that is. I'll write it down here on the right hand side. I'll write it in terms of x because this is how you've probably seen it in your tables. The integral of 1 over x squared plus a squared dx is 1 over a arctan x over a plus c. And so I'm almost in the right form here, but instead of an x, if I had a y, I could just integrate this immediately, but I've got a y minus 1. So what I can do, you could do this all in one go if you know what you're doing, but I'm going to take it slowly, and what I'm going to do is let y minus 1 equal z, let's say, another variable. And I'm going to use a simple substitution in order to evaluate this integral. Hopefully you can see from this that dz by dy is just 1. So in fact, the left-hand side, when I come to change variables, I get, instead of the y squared minus 1, I get z squared. And then I have a plus 1 at the end. And instead of dy, I just have dz. So this I can now integrate immediately using the standard result. A squared is just 1, so a is 1. So what I in fact end up with is just arctan of z, plus another constant of integration, so I'll just call that c1 for the moment. And now I can change back into my old variables. So z is y minus 1. And as I said, you might have been able to do that without the substitution. That's fine, but I've done it more slowly just so that we can be sure. So what we now have to do is go back and put the left-hand side equal to the right-hand side. Arctan of y minus 1 plus 1 constant equals, and if you remember what was on the right hand side before, x squared over 2 plus another constant. And what I can in fact do now is combine the two constants. This is so standard that sometimes you won't even see the two constants separately. You'll just see a single constant of integration. But basically what I'm saying here is that my constant k is c minus c1. It's just a new constant. So in this case I can now take the tan of both sides, remembering that I have to tan the whole of the right hand side in one go. And I could simplify that right hand side now further using an identity for tan of a plus b, but that I think would make things look worse, so I'm not going to bother. I can, however, for my final statement, just add 1 to both sides, and I may as well do that so that I have in fact made y the subject. And that is the general solution to the original differential equation. I have not found the value of the constant k because I haven't been given an initial condition, so I can't proceed any further, but that is the solution to the original differential equation. If you wanted to, you could check that was right by differentiating it and substituting this solution back into the original equation, and you should see that it satisfies it.